Okay, let's dive right into this explainer. You know that incredibly frustrating moment when you're walking downtown, you pull out your phone to check directions, and suddenly your little blue dot just completely freaks out, like it jumps 3 blocks over, puts you right in the middle of a river, or insists you're inside a coffee shop you've literally never been to? It is so annoying. But why does that actually happen? Well, the secret behind this map madness lies in a concept called DOP, or dilution of precision. Today, we're going to completely decode the geometry of GNSS, Global Navigation Satellite Systems.
To guide our journey today, I want you to keep this specific question in the back of your mind. Have you ever noticed that your GPS is actually pretty good at telling you what street you're on, but it's absolutely terrible at telling you what floor of a building you're on? The answer to why your vertical accuracy is almost always worse than your horizontal accuracy, it lies entirely in a geometric secret that we're about to uncover.
Here's our quick roadmap for today. We'll start with the urban canyon mystery, define what DOP actually is, explore the intersecting spheres analogy, compare good versus bad geometry, tackle the math and misconceptions, and finally, look at the real-world GNSS impact.
All right, part 1, the urban canyon mystery.
So we kick things off with a scenario pretty much everyone knows all too well, the dreaded urban canyon. You're standing right between these massive, towering skyscrapers, looking down at your device and watching your signal absolutely panic. Now, when this happens, users almost always assume, my receiver must be cheap, or, man, the signal is just too weak. But here is the massive secret that's going to totally change how you understand navigation. It's not your receiver, it's not the signal strength, it's the geometry. It is entirely about exactly where the satellites that your phone can physically see are located in the sky at that exact moment.
Which brings us to part 2, what DOP actually is.
To really understand this, we need to clearly define the main character of this explainer. This concept isolates one specific cause of error, totally separating it from everything else going on in the atmosphere or inside your phone's hardware. So DOP, or dilution of precision, is a scaling factor that dictates how much satellite geometry will amplify position error given the same measurement noise. And I really want to emphasize that word, amplify. See, DOP is not an error itself, it's a multiplier. Think of it kind of like a magnifying glass. If there's already a tiny bit of noise or uncertainty in your signal, a bad DOP will act as a massive scaling factor, and it just blows that tiny error up into a huge city block-sized mistake on your mat.
This distinction is absolutely crucial. DOP depends purely on satellite geometry. That's it, the physical arrangement of the satellites up there in space. By stripping away all the other noise, we can clearly see that DOP has literally nothing to do with atmospheric interference, ionospheric delays, signal strength, or even how incredibly expensive and high-tech your receiver is. It is pure, unadulterated geometry.
Let's move to part 3, the intersecting spheres analogy.
Numbers and definitions are great and all, but to really grasp this, we need a physical interpretation to build that intuition. I want you to just imagine looking up at the sky. Think of each satellite your phone connects to as providing a directional constraint. Picture that constraint shaped like a giant invisible sphere expanding outward from the satellite all the way down to you. Your true position on Earth is the exact single microscopic point where all these giant satellite spheres intersect.
And this brilliantly illustrates the core intuition of our explainer. If those giant spheres intersect at sharp, distinct angles, they lock you into a highly precise point. The area of uncertainty is tiny. This is what we call low DOP. But if the spheres are coming from roughly the same direction, they intersect in a shallow, flat, overlapping kind of way. This creates a massive, smeared region of uncertainty. You could realistically be anywhere inside that large overlap. And that, my friends, is high DOP.
Let's see this in action in part 4, good versus bad geometry.
Let's take this intersecting spheres concept and look at what good and bad geometry actually looks like up there in space. The contrast is massive. In an ideal geometry scenario, the satellites are beautifully spread out wide across the entire sky. They have high elevation diversity. Some are directly overhead, some are way out on the horizon. This gives us those perfectly sharp intersections and a position DOP, or PDOP, of about 1 to 2, which is absolutely excellent. But contrast that with poor geometry. Here, the satellites are all clustered in one tiny region of the sky, maybe because a giant building is blocking the rest of your view. This creates those flat, shallow intersections, resulting in a terrible PDOP of over 6 and sometimes even over 10.
Which actually brings us right back to that question we posed at the very beginning. Why is vertical error almost always larger than horizontal error? Why does your GPS know your street perfectly, but completely fail at guessing your floor?
Well, the answer is simple and honestly mildly tragic. It's because most satellites are above us. Think about it. To get sharp vertical intersections, you would need satellites directly above you and directly below you. And unfortunately, we just haven't figured out how to put navigation satellites underneath the Earth's crust yet. Because they're all up in the sky, they provide very strong horizontal constraints, but inherently weak vertical constraints.
Moving on to part 5, the math and misconceptions.
Okay, we've built the physical intuition, so let's briefly peek at the actual math behind this, just to clear up some incredibly common myths. For the geeks out there, the math shows exactly where DOP originates. After linearization, the GNSS system becomes a standard equation, and taking the least square solution gives us an estimation covariance matrix. DOP values are mathematically derived directly from the diagonal elements of this very matrix. But hey, don't panic, we really don't need to memorize linear algebra to understand the brilliant results it gives us.
We can break down what feels like a total alphabet soup of acronyms pretty simply. That covariance matrix basically allows us to slice up the geometry into different areas. GDOP covers the whole shebang, 3D position and clock time. PDOP is just your 3D position. HDOP is purely your horizontal x and y axes, while VDOP isolates your vertical z-axis. And finally, TDOP zeroes in on just the time aspect. It's a perfectly segmented way to figure out exactly where your geometric weaknesses lie.
Now, between you and me, there is a lot of really bad information out there about GPS. So I want to quickly debunk some of these pervasive myths. First up, more satellites always improves accuracy. Absolutely false. Throwing 10 more perfectly clustered satellites into the exact same tiny patch of sky isn't going to help your geometry at all. It might actually just give you more of the same bad data. Second, DOP is an error. As we just learned, totally false. It's just a scaling factor. And finally, DOP depends on measurement noise. Also false. The noise is entirely separate. DOP just magnifies it.
So, the crucial point we arrive at is this beautifully simple takeaway equation that links everything we've talked about together. Your final, real-world position error is approximately equal to your DOP multiplier multiplied by your baseline measurement noise. That's it. The entire concept distilled into one truly elegant line of math.
Let's actually look at that math in action. If your receiver and the atmosphere are giving you an inherent measurement noise of, say, 3 meters, and you have a beautifully spread out satellite geometry giving you a PDOP multiplier of 2, your total position error scales up to exactly 6 meters. But what if you walked right into a tight urban canyon and that PDOP spiked to 10? Well, suddenly your 3 meters of noise becomes 30 meters of error. And boom, that is exactly why your map dot jumps.
And finally, part 6, real-world GNSS impact.
Let's wrap this whole explainer up by seeing how this invisible geometry directly impacts the tech that we literally rely on every single day. This one single geometric concept explains so much. It tells us exactly why tall buildings that block your sky view totally ruin your positioning. It also perfectly explains why modern phones use multi-GNSS, meaning they connect to GPS, Galileo, and GLONASS all at the exact same time. It's not just about having more satellites, it's about having access to satellites in totally different parts of the sky to force a wider geometry and a much lower DOP. It also forces engineers to be really smart about which satellites a receiver actually chooses to listen to.
I'm going to leave you with this final provocative thought to ponder. As we launch thousands of new satellites and our skies fill up with more and more multi-GNSS constellations, can we ever completely mathematically eliminate geometric error? Or, simply because we can't put satellites beneath our feet, will the sheer physical presence of the Earth always get in the way of perfect vertical precision? I really hope this explainer has completely transformed how you look at the invisible architecture of satellites guiding you every single day. Until next time, keep looking up.